In this video, I'm going to be doing a bunch of true or false problems on infinite sequences and infinite series. So if you're studying for a class that involves this topic, hopefully this video can be of help. So I actually took all these problems from old exams or old study guides or old sample exams, which usually the sample exams are actually old exams, from an old UCI class that no longer exists. This class, I think was Math 2J back then, used to teach infinite series and like some linear algebra. But now the infinite series portion of this old class, this class that no longer exists, got moved into the current Math 2B as of the filming of this video. So this can be a study tool if you're studying for the Math 2B final. All right? These are, again, previous exam questions possibly, so you can expect this level of difficulty on the final exam of Math 2B if you're here for that class. All right? And typically, true-false problems are tricky, actually. There's some maybe small detail that they might have changed, and then it's testing if you can spot that small difference such that it makes the statement false. Okay, so these true-false questions can get tricky, so we got to pay attention to the details very carefully here, and we got to, of course, know the concepts really well as well in order to succeed in these true-false questions. Okay, so with that said, let's begin. And for all these questions that I took from these old exams, no justification was required for whether you put true or false as your answer. So you have a 50% shot from the get-go to get full credit on each one. Of course, I'm going to go over why it's true or why it's false to help you understand the concept that it's trying to assess, okay? So, I don't know if I said this already, as always, you should try the problem first on your own and then come here, so pause it, try to think through it yourself after I read the problem, and then unpause it to see the solution, or at least what I thought is the solution, okay? So, no guarantees that I got all of these correct, so I want to put that disclaimer out, but I'm pretty confident in my answers, and hopefully this can help you with your thought process if you got stuck or you got confused, okay? So number 1A, I should say, we have this summation as n goes from 1 to infinity, negative 1 to the n over square root of n. It's saying that this series converges. Is this true or is this false? So go ahead and determine your answer. The answer is true. How do we know that? We can use the alternating series test. This one you can quickly eyeball. What does the alternating series test say? Well, if you get rid of the changing sign, first of all, 1 over square root n is a decreasing sequence. Okay, and the limit as n goes to infinity of 1 over square root n is 0. So therefore, by the alternating series test, this guy converges. Okay, this one, we started off quite simple, hopefully. Next, this one's actually even simpler. This series diverges. Is it true? Is it false? It's true because it's a harmonic series, or a p series with p equals 1, which we know diverges. Next, if summation as n goes from 1 to infinity, absolute value of a sub n is divergent, then summation as n goes from 1 to infinity of a sub n is divergent. Is this true? Is this false? So go ahead and pick your answer. The answer is, if I even don't remember what I put as my answer, so let me think through it live, like I'm on the exam. This is actually, if we think about what conditional convergence is, this violates the definition. Or it's not always true. Because let's actually remember what conditional convergence says. It says that if this guy is divergent exactly, but this guy over here is convergent, so without the absolute value, then that's called conditional convergence. So it's possible that this original guy, or not original, this guy without the absolute value is convergent. That's called conditional convergence. So this is false. Okay, and that's exactly what I said over here. Okay, And we could also just think of a simple counterexample. A counterexample is an example that proves the statement false. And it's the alternating harmonic series. Negative 1 to the n power over n. That's for sure divergent if we get rid of the changing sign, if we absolutely value it, because it becomes this, which we know diverges. But we know also the alternating harmonic series converges with the alternating sign by the alternating series test. Okay, so you can think of a counterexample, totally fine, or you can remember what conditional convergence is. Next, if limit as n approaches infinity of a sub n equals 0, then summation as n goes from 1 to infinity, a sub n is convergent. This is for sure false. Counterexample, the harmonic series. Okay? This is trying to trick you in that we know that if the limit is not equal to 0, we know for sure this guy is divergent. That's the test for divergence. Okay? If the limit is 0, then there is a chance for the series to converge. It's not always the case. For example, the harmonic series, it diverges actually. But in order for the series to possibly converge, this has to be 0. That's what the test for divergence says. Okay, next, summation as n goes from 0 to infinity, 1 over 7 to the n power is this 7 over 6. Okay, so this is a geometric series, so we got to find the sum of it. Infinite geometric series. We know how to find the sum of it. Hopefully you know, because there's a nice, easy formula. It's, the common ratio is 1/7, by the way, so the sum is the first term, so that starts when n equals 0, so 1/7 to the 0 power is 1, first term, over 1 minus common ratio. You do the math, it's 7/6, so it's true. Okay, no tricks here in my opinion. You just have to know how to find the sum of an infinite geometric series. This one, summation as n goes from 0 to infinity, pi to the n power is equal to 1 over 1 minus pi. This is false because the series diverges. The common ratio pi is greater than 1, so it diverges. Remember, for a geometric series, the common ratio, absolute value of the common ratio, I should say, needs to be less than 1 for the geometric series to converge. Pi is 3.14159, whatever. That's clearly greater than 1. So series diverge. You can also imagine you're adding an infinite number of 3.14 whatevers, and to some power. It's for sure going to diverge. And we kind of did the test for divergence as well. Limit as n goes to infinity of pi to n. That's for sure blowing up to infinity. So again, that test would have told us that this series diverges. Next, the ratio test can be used to determine whether summation as n goes from 1 to infinity, 1 over n cubed converges. Is this true? Is this false? So I would just directly try the ratio test right away. And I remember what I wrote for this. It's false. So this is the procedure for the ratio test. A sub n plus 1 divided by a sub n. So replace n with the n plus 1 and multiply by the reciprocal of this. If we take the limit as n goes to infinity, this is 1. This guy expands out to n cubed plus who cares. The biggest degree on top is 3. Biggest degree on the bottom is 3 as well. So since they're the same, take the ratio of the leading coefficients. So that's 1 over 1, which is 1, okay? The ratio test says that if the limit is 1, it's inconclusive, actually. So we can't use the ratio test to determine whether this guy converges or not. It's inconclusive. Okay? That's number 1. Okay, now let's move on to number 2, another whole set of problems. Okay? Determine whether true or false for this one now. If 0 less than or equal to a sub n, less than or equal to b sub n, and this series with b sub n converges, then this series with a sub n converges. Is this true? Is this false? Well, if bn converges, an is even smaller than bn, so an must converge as well. That's the comparison test. Okay? So true. Next, so same thing, an is positive and it's less than or equal to b sub n. If B sub n diverges, then A sub n diverges. Is this true? Is this false? I believe this is false because if B n diverges, something smaller could possibly converge. So not always true that A n diverges. It could diverge, but we don't know. It's, as I said, something smaller could possibly converge now. Okay? So I even said the comparison test would work here if AN and BN were swapped, in that if we know that AN diverges, since BN is even bigger, then it must diverge as well. Okay? So again, as I said toward the beginning, true false is testing if you know these small details well a lot of the time. And they try to trick you purposely. And they swap the detail a little bit. So if they swap this, it would be true if this AN and BN here were swapped. But if they write it like this, then it's false. So again, you have to pay attention to the small details. And again, as I said also in the beginning, you have to know that comparison test well in order to be able to understand this properly. Okay. Next, we have this weird summation that goes from 0 to infinity. 2 to n over n factorial is equal to e squared. Is this true? Is this false? So at least for Math 2B, I believe that this might be quote unquote considered a more challenging question because they only teach the Taylor series at the very last lecture. So they might not, there's a low chance, in my opinion, that I'll ask you something like this, but it's possible because you learned the Taylor series. So it's possible that you could get this. So with that said, if they're asking you this question, they probably are expecting that you know how to find the sum of it. So which types of infinite series do we know the sum of? We know how to find it for a geometric series. If it's a telescoping sum, we know how to find that. And if it's a power series, specifically like one of the Taylor series that you might want to memorize, we know how to find the sum of that also. Okay, so does this look like any of the Taylor series? So for the course Math 2B, I would recommend memorizing the Taylor series for e to the x, sine x, and cosine x. Those are too bad to memorize. And for sure, if you're taking more science, engineering, physics, whatever math classes in the future, you have to know them anyway. This looks, just go by this side over here. Doesn't it look like e to the x? What's the Taylor series for e to the x, or the Maclaurin series for e to the x? It's x to the n over n factorial. What's the difference? The x is 2. Remember, we can represent functions as a power series, so this power series, you can treat it like a function. Wherever there's an x, plug in 2. So e squared is, that's x is equal to 2. 2 to the n over n factorial, that's exactly that. So it is e squared, so true. Again, the trick here is, it has to be a series that we know how to find the sum of. There's only so many that you learn up to this point. Geometric series, telescoping sum, Taylor series. That's honestly the few that I can think of off the top of my head as a tutor for this course. So you got to use one of those. This one looks like e to the x, so use that one. And the clue was e squared as well. Okay, that's how to think through that, in my opinion. Okay, next, 1 to the x plus 2 to the x plus 3 to the x plus dot 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 is a power series. This is true or false? What do you think? This is false. Not even a power series. Power series should be like an infinite polynomial. X to some power with some coefficient out in front, like x cubed plus 4x to the 4th power plus 100x to the 5th power minus 10,000x to the 10,000th power, something like that. It has to be like in a form of a polynomial. This is in forms of exponentials, not even a power series. That one should have been easy. Okay. If p sub 3 of x equals 4 plus 2x minus x squared is the second degree Taylor polynomial of a function f at a is equal to 0, then f prime of 0 is equal to 2. Okay? Actually, I don't think you learn about Taylor polynomials anymore in Math 2B. They skip that section. So if you don't know this and you're in Math 2B as of the current filming of this video, you should be fine. I believe this is false though. It should be -2. So I won't go over why in this video, but basically, I'll quickly go over why. At the center of the Taylor series is nice when we evaluate at the center, the function or its derivatives, because most terms in the power series would go to 0. The only non-zero term is some constant, usually. And if we... Actually, I did not even get it right. If it's a second-degree Taylor polynomial, then the term we're interested in for f prime is the coefficient out in this term. So actually, this is true. My bad. I don't know what I was thinking. This seems to be true because... Remember, okay, let me just explain this if you're curious. Taylor series, summation as n goes, the infinite Taylor series is f to the nth derivative, this is centered at 0, so I'm going to write it like that, x to n over n factorial. Okay? So, f prime of 0 would be when n is equal to 1, right? So that's why we look in front of the x to the first power term. Okay, and 1 factorial is just 1, so what's the coefficient out in front? It's 2, so that has to be this first derivative at 0. So that's true, actually. My bad. Okay, if I confused you, sorry about that, but it's true, okay? Again, I can't guarantee all my answers are correct in this video. I didn't have an answer key for half of them. So do check my work, and of course leave a comment if you got a different answer, and we can discuss in the comments. I might be wrong for some of these. Okay, if the sequence a sub n is decreasing and a sub 4 is greater than 4 for all n, then a sub n is convergent. Is this true or is this false? This is true. Why is that? This is decreasing and it's greater than 4, so you can imagine that it's like a horizontal asymptote if it's like a function. A function can decrease but keep decreasing but approach a value. That's asymptotic behavior. So it's possible for sequences as well. It's just not continuous at every single point. It's at discrete values, but it can still have that behavior where it's slowly decreasing to 4 but still be greater than 4. Okay? So that's true. And I guess it's by that monotonic sequence theorem, if I got that, remember that name correctly. Okay? So I even put a note, this is a sequence, okay? Don't confuse this with an infinite series, in which case it would be divergent. We're not summing up the terms here. This is a sequence. A sequence is a list of numbers. And this list of numbers would eventually converge to 4 probably. Okay? We're not adding all the terms, in which case you're adding like an infinite number amount of values greater than 4. That will for sure diverge. Okay, so don't confuse this sequence with a series, is my point here. Next, if, you might have seen the answer already, if a sub n is positive, summation as n goes from to infinity, a sub n converges, then summation as n goes from 0 to infinity. I don't know why. Did I make a typo? Probably a typo. Let's assume they both start at the same point. It doesn't matter if it's 1 or 0. Probably n equals 1 to infinity, minus 1 to n, a sub n converges absolutely. Is this true? Is this false? It is true by definition of absolute convergence. If we take the absolute value of this guy, that changing sign goes away. And we know that it's convergent. Therefore, that's absolute convergence by definition. Yep. Next, if 0 less than alpha, less than 1, then limit as n goes to infinity, alpha to the n power is 0. That is true because if it's bigger than 1, that's an exponentially growing function. If it's between 0 and 1, that's an exponentially decaying function. You can think of it like that. Or from experience, if you plug in like half, alpha is half, then for sure you keep halving, so it's getting smaller and smaller. Okay? Even if it's like 9/10, 90%. If you keep taking 90%, it's getting smaller and smaller. So this limit is true. You can think of it like that as well if you want to. All right, number 3. I believe this is written by a different teacher now. So you might actually see some of the same questions or very similar. Okay? But this is still good practice because, again, sometimes they change some really, really small detail and it makes the result completely different. Okay? So number 3A, let's get on with it. If the series, this guy, pay attention to absolute value probably, a sub n converges, then this series, a sub n, must also converge. This is true by absolute convergence. This is by definition. Okay? So again, as I just said, there's going to be repeats of some problems, probably a very similar one. So we've got to pay attention to the details. If the series summation as n goes from 0 to infinity, b sub n converges, and this looks familiar, right? Then the series, this guy must also converge. So if bn converges, should an converge the series? It should, because an is smaller than this, and we know this converges, so something smaller must also converge. That's the comparison test. Does this guy converge here? True, false? It does not converge. So this is false. The common ratio, opposite value, is greater than 1. So it diverges. This is a geometric series if you didn't catch that. Does this series converge or diverge? This strange looking series. Okay? So this one, we got to think a little bit here. It's not a typical series that we've seen before, probably. Okay? So maybe we can do a quick comparison test. All right? This is square root of n plus 1 minus square root of n. Would you agree that this is smaller than just square root of n plus 1? Hopefully you do, because here you're subtracting something, so it must be smaller than without subtracting something, okay? If we take that series of just this guy, put this, or imagine that's gone, does this series converge or does it diverge? This one we've seen before, hopefully, or it looks more familiar. It's quite, actually, we already know from this, from the test for divergence, that this will diverge. The limit as n goes to infinity of this guy is infinite. So the test for divergence says this would diverge. Since this diverges, and this guy's even bigger, by comparison, it diverges as well. So, this would be true, okay? I did it a little differently, I guess, over here. I said that this does diverge because it's a p series with p is negative half, which is less than 1. P series needs to be greater than 1 for it to converge. This is a p series with p is negative half, so it diverges. And again, since this diverges and this is even bigger, this guy must diverge as well. Okay, comparison test here. Okay. That's how I thought through that one. Does this series diverge? True, false? It's true. Hopefully this one's a quick one. Do the test for divergence. The limit as n goes to infinity of 1 minus 1 over n squared. That's 1, which is not equal to 0, so it diverges. Okay? Next. If the series summation as n goes from 0 to infinity, a sub n converges to s, then the series summation as n goes from 1 to infinity, a sub n converges to s minus a0. Is this true? Is this false? This is, hopefully this one's easy, true, because you're just starting from the next term instead of starting from 0. So you subtract the very first term, s minus a sub 0. Exactly. Okay. Next, if the series an and the series bn both converge, then limit as n goes to infinity, a sub n over b sub n equals l for some non-zero real number l. Is this true? Is this false? This looks familiar to me. Looks like the limit comparison test, something to do with that. Okay, but you got to be careful. This is where the small details matter here. Okay? What does the limit comparison test say? If this is, yeah, exactly, greater than 0 and less than infinity, so non-zero and finite number or real number, that's fine. If this converges as well. If this diverges as well. So if you just have that understanding, you would think it's true, but this is actually false. Why is that? Basically, this is term for this. I don't remember what the converse, if I remember correctly. The limit comparison test says if this, then both diverge or both converge. This flipped it. It flipped the condition and the conclusion. You can't always do that. It's not always true. Sometimes it's true, and there's another term for that. I really don't remember the terms. There's a term when if you flip it, then if you're able to flip it and it's still true, there's a term for it. But it's not the case here. They flip the condition and the conclusion. This is the conclusion, or a possible conclusion for the limit comparison test, and they're putting it as the condition now. You can't go backwards in this case. We can easily think of a counter example, actually, if you didn't realize that. So to make your life easy in a lot of these, if you can think of the simplest counter example to prove it false, then you're good. So let's keep things simple. What if I picked one to be 1 over n squared and the other to be 1 over n cubed? Okay? That's what I thought of. Then this limit would be, it will simplify to limit as n approaches infinity of n, which is clearly infinite. Okay? We know these two converge, but this limit does not exist. We found a counterexample right here. It's not always that it's some finite number L that's positive. Okay? Again, this is, again, trying to test that whether you know that you can't flip the condition and the conclusion of the, which test was it? Limit comparison test. Okay? And we found a counterexample easily. So usually, again, to hopefully hammer the point in, if you can find just the simplest counterexample to prove this false, you're good. Okay? Moving on. Hopefully you didn't see any of those yet. Whoops. And that's the next page. Let's do a better job with hiding these. Okay. If you saw it, that's fine. If the function f is continuous, positive, and decreasing on the interval 1 to infinity, and integral from 1 to infinity f of x dx converges, then the summation as n goes from 1 to infinity, f of n converges to the same value. This is for sure false. Hopefully you thought of that right away. It does not necessarily converge to the same value. It could, but probably not. You can imagine an integral is continuous. There's values between 1 and 2, like 1.1, 1.001, 1.000000001. There's infinite values. This one, you're summing 1, f of 1, f of 2, f of 3. So there's less. It's still an infinite amount of values, but you're summing fewer values. Or I should say less values, because you can't count that, just to be grammatically precise. So if you think about it like that, obviously this one's likely to be smaller if it does converge, okay, versus this one, okay? Next, if the power series, what is that? Okay. If the power series summation as n goes from 1 to infinity, c n x to n converges for x is equal to 1, then it must also converge for x is equal to negative 1. This is true, this is false. Can you think of a counterexample to prove this false? Or is there some other additional understanding that we can think of to prove that this statement is false? So, this is what I thought of. This is false, by the way. Let's assume the radius of convergence for this power series is 1. Where is this power series centered at? It looks like it's centered at 0, because it's not like x minus 1 to the n, where the center would be 1 then. It's x to the n. So it looks like it's centered at 0. So let's hypothetically make a situation where the radius of convergence is 1. Okay? Meaning, our interval of convergence, we don't know if it includes the endpoints, but it's between -1 and 1. Okay? Remember when you do when you're finding the interval of convergence, you have to check the endpoints, and hopefully you've seen some problems where one endpoint sometimes works and the other doesn't. Okay? So, with that experience and knowledge, we can already say that this is false. It could converge at this endpoint, but it could diverge at the other endpoints. So, that's how I thought through this one. Again, you could probably think of an easy counterexample. I did not, though. I immediately, for some reason, thought of radius convergence because it's symmetric. That's probably why. And then I thought of, well, usually when we find interval convergence, we have to check those endpoints precisely because the ratio test is inconclusive there. So from experience of doing all those problems, I thought of that. Okay, so that's one way to think of that. If you like that, better than finding a counterexample. Okay, if the series this guy converges, then the terms of this guy must converge to 0. Is this true? Is this false? This is true. Test for divergence says this, right? If this converges, if this is what does the test for divergence say? It says if this diverges, then this guy diverges as well. It doesn't say that if this converges, then this converges as well. It never says that. It says that if this converges to 0, or we know that if this converges to 0, there's a chance for this to converge. Okay? But if there's a series that for sure converges, then the terms have to for sure go to 0. There's no other choice. If you think about it, you're summing up an infinite amount of terms. So if this infinite sum converges, you have to be summing up terms that approach 0. There's no other way. You can think of it like that as well. Okay. So the test for divergence doesn't directly state this. Maybe I should clarify that, but we thought through it. All right, now last page of problems, I should say. Does the series converge conditionally or absolutely? This is probably what this is asking. Is it true or false? Or maybe it's not all convergent, actually. My bad. So let's just focus on if this is true or false. Does this converge conditionally? Does it not? It actually converges absolutely. Because if we take the absolute value, the changing sign goes away. This guy is a P series with P equals 2. Converges. We know that. So since this absolute valued version converges, we call that absolute convergence. Conditional convergence is when this absolute valued version diverges, but the original guy converges. That's conditional convergence. Okay, if this sequence is bounded and increasing, then it must converge. Is that true? Is that false? I believe we just did a similar problem not long ago, right? True. Again, think of horizontal asymptote. Okay? It can keep increasing, but it'll slowly increase to a value, like a asymptotic behavior. Okay? If the series this guy diverges, and an is positive, which is less than or equal to b sub n for all n, then this guy must also diverge. Is that true? Is that false? This is true by comparison test. This diverges, this is even bigger, must diverge. Okay? If the series converges to L, then this series converges to L plus 3. Is this true? Is this false? I can already tell you right away, this is false. It diverges, actually. Because imagine you're summing up an infinite amount of 3s. So you can use that property where you can kind of distribute that summation sign to both. So you're summing up an infinite amount of 3s. For sure, it's going to blow up. Okay? Does this guy converge or does this diverge? This is true. This is false. This is if I remember correctly, is true. So you can perform a telescoping sum. So a telescoping sum, you should always try when it's like something like this. A difference of terms and like rational function looking like. Okay. So I just listed out a bunch of terms. So n equals 1, you would get these two terms. N equals 2, you get these two terms. N equals 3, you get these two terms, so on and so forth. You'll see that if you start canceling things out, what doesn't get canceled is this minus 1 over here and this minus half over here. So this 1/3 gets canceled with this minus 1/3, 1/4 with this minus 1/4, 1/5 with this minus 1/5, so on and so forth. So these two terms never got canceled. So there is a sum. We don't care what the sum is. It just asks if it converges, which it does, because there's a sum, a finite sum. Given the sequence a sub n, if the sequence a sub 2n and a sub 2n plus 1 both converge, then a sub n, the original, must converge. Is this true? Is this false? This one, it's probably a good idea to try to think of a counterexample right away. Can we make a simple one? This is a sequence. It's just a list of numbers. Can we make an infinite list of numbers that can prove this wrong? We can. Just imagine if the sequence is -1 to the n. So -1, 1, -1, 1 alternates. And precisely, I said it alternates because 2n means every other term. So in this case, you would get just 1, 1, 1, 1, 1, so on and so forth. So that sequence converges. It converges to 1. This one takes every odd term. So it would be -1, -1, -1, -1, so on and so forth. For sure, it converges to -1. Okay? This guy, though, the original guy, this counterexample that I thought of, for sure does not converge. It oscillates between -1 and 1, so the limit never exists. Does not exist. So it does not converge. So we thought of a simple counterexample. Okay, so usually you want to keep things simple. Don't make things complicated. Okay, usually a simple counterexample can throw something like this off. Okay, now to the back, to the final ones. This series converges and an over bn approaches 0 as n approaches infinity. Then the series must also converge. So again, this looks something to do with the limit comparison test. Is this true? Is this false? So again, maybe it's helpful to think of a very easy counterexample. But this time, maybe let's work backward. Let's assume this is false. So these are the conditions, this is the conclusion. What if the conclusion is the opposite, that it diverges? So what's a series that diverges? Let's choose 1 over n. Okay, so again, keep things easy. So if an is 1 over n, which we know diverges, so it's opposite of this already, so we want these still to be true. So can we get a bn such that bn converges and then an over bn approaches 0 as n approaches infinity? So that's why I said here, what bn would make this true? And bn itself, the series, converges. Okay, so if we chose that an to be 1 over n, we want this limit to be true. So what can we think of a bn that would make this true? That also converges. How about this one over here? This one you might have to spend a little time to do some extra thinking. This one's not as obvious, but again, try to keep things simple. This one's not as simple, but quite simple still. So let's check that this limit is true. Well, for sure we know this is true because this converges by the alternating series test, by the way. Okay, so now let's check this portion over here. Here we have to recall that if limit as n goes to infinity of this guy equals 0, I should say, then this guy equals 0, which converges as well. Okay? So now let's go through the motions. of finding this limit with this guy over here. So get rid of the alternating sign because of this absolute value. Okay, let's algebraically manipulate this to this because when we divide by a fraction, we multiply by the reciprocal. Okay. Now this can simplify to 1 over square root n. As we take n to infinity, the value approaches 0. Okay. By this, since this absolute value version approaches 0, the original guy also approaches 0. So we found that this is false. To recap one more time, let's assume that this is false first, and let's try to find a counter example. What is a series that we know diverges? The harmonic series. So let's let an be 1 over n. Okay, then we have to make these two true still. We have to find a bn that makes these two true. So I chose this one because we know this converges by the alternating series test. And then if we go through the motions of finding the limit, it was actually 0. Okay, so we found that these two conditions were met with this choice and this choice, but this one was not met, or the conclusion was not correct, so it's false. Okay, so this one, probably easiest to think of a counterexample. Does this guy converge? True, false? This one should be quick. True. Because this is a p series with p equals 1.1, which is greater than 1. Okay? Don't be confused. P series is 1 over n to the p. That's the p. So p is 1.1 here. If the power series, this guy, converges absolutely at x is equal to -2, then it must converge absolutely for x is equal to 2. This is true. Is this false? I believe this is true. Because let's consider absolute convergence. You put absolute value signs there, okay? It tells us that this is absolutely convergent. Okay? If we do some algebra, that changing sign would go away. So we have this over here, which is equal to this. Okay? And at x is 2, it's already positive. So it's exactly the middle over here already. So, because it tells us that it's absolutely convergent at x is -2, these three are true then, or this equality is true. Okay? And at x is 2, to check for absolute convergence, that's the middle over here, which we already know converges from the first part, what they gave us. So this is true. Hopefully that made sense. Okay. I think it might be the last one. Does this series converge to 4/3? This is a geometric series, so we can find the sum of it and check. It's false because by properties of exponents, you could rewrite it like this. Okay, 3 to the -1 power on the bottom is the same thing as 3 on top. Okay, so this is the common ratio, 1/3 to the n. You can rewrite it like that if you really wanted to. So the sum is first term, n equals 1 is the first term. So 1/3 over 1 minus common ratio, due to math, it's 3 times half, which is not 4/3. Okay, and that's it. So hopefully this was a good practice set if you're studying for the final exam. Again, it really tests the details of the concepts that you should know in this class. All right, please like and subscribe if you found this helpful in any way. If you have any questions on any of these problems, feel free to leave it in the comments and I'll try to get to it.